Hello, I'm Davey, and today we're going to be talking about how to find the surface area of the graph of a function, which if you think about it is kind of one of the more accessible problems in math, right? Because this is something that you learned way back in like elementary school, probably like formulas for the surface areas of, cones and spheres and simple things like that. And obviously there was no proof given, I'm sure not even any kind of argument. You just heard things, everything had a pi in it, or a 1/3 for some reason, whatever. Or calculus, finally lets you derive all these formulas. I'm not going to do that all in this video, but we'll look at one example of a simple surface, not one you would have encountered in elementary school, I guess, but a surface that's pretty simple nonetheless, and how we can use calculus to find the surface area of, well, in this case, just a certain special portion of that surface. Okay, so how is the surface defined in this problem? Well, it's not defined intrinsically. It's not defined by just what the surface is shaped like. It's defined by the fact that it's given by a specific equation in the xyz coordinate system. Specifically, it's given in the form z equals a function of x and y. Z equals 2 plus x squared plus y squared. Ignore that thing for now that I'm putting a box around. I'll explain what that is in a second. But yeah, the equation of the surface is z equals 2 plus x squared plus y squared. And we're interested in not finding the area of the whole surface for this problem, but the area of the part of it that is above a certain region R in the xy plane. It's shadow, right? Every region of the surface drops down to some region in the xy plane, and we're defining a region of the surface via a drop-down region in the xy plane, and then we want to find the area of that part of the surface. So what's the drop-down region? Well, it says it's bounded by 4 things, 2 of which are circles, 2 of which are lines. And we know what they are just from the equations, right? X squared plus y squared equals something is always a circle, but remember the something is the square of the radius, because by the Pythagorean theorem, x squared plus y squared is the distance between a point xy in the xy plane and the origin 0, 0. X squared plus y squared, right? The two legs squared, summed. So this says x squared plus y squared equals 2, for example. The first equation says that, okay, the distance between this point xy and the origin squared is 2, right? Because the Pythagorean theorem says x squared plus y squared is the square distance, the hypotenuse squared, right, between the point xy and the origin. So this equation tells you that the square distance between the point xy and the origin is 2. So that means the distance is square root of 2. And similarly for the second equation, the actual distance between xy and the origin is 2. So the radii are root 2 and 2 respectively. And I've graphed these two circles here, as you can see on the left, hitting the x-axis at the points root 2, 0 and 2, 0. But we're not interested in the whole annulus between these two circles. We're only interested for some reason in the part of it, the sector of it bounded by 2 lines through the origin, namely y equals x, your old 45-degree friend between y and x-axis, and x equals 0, which is just the y-axis. Okay, and did I say those right? I did. Okay, those are the 2 lines, and those are the 2 circles. Great. Okay, so now that's what the region R is. Now, what does the part of S lying above R look like? Well, S, as it turns out, is a paraboloid. It's clearly some kind of 3-dimensional surface. Why is it related to parabolas? Well, sure, it has a square in it, but circles also have squares in them. And, hyperboloids, ellipses can, if you did conic sections, whatever. So why is it a paraboloid specifically? Well, if you look at any plane, like I'll draw the plane I'm talking about here, any kind of vertical plane, you take a cross section. If you look at like the x equals 2 plane, that's not a very good drawing, but the x equals 2 plane would be parallel to the x equals, or I guess that's the y equals 2 plane that I drew there. So I'll just change this here to align with that, or y equals something plane. You can pretend it's the y equals 2 plane if you believe that that plane is, hitting the y-axis at y equals 2 anyway. So if we look at any plane like that, if we substitute y equals 2 into the equation, right, and see, to find the cross-section of the surface with that plane, what we do is we substitute the conditions of the plane into the equation and see what's left, what of the surface is left, and that gives us, right, what portion of the surface is in the plane, which is the cross-section. So if we know y equals 2, right, and we're looking at what the surface looks like there, then what's the equation? Well, it's z equals, well, let's see, we have, what was the equation? 2 plus x squared plus y squared. So, okay, actually it would be 2 still here, not 4. It would be 2 plus, and now y equals 2. I see, that's what I wrote before. Okay, y equals 2 gives us y squared equals 4 plus x squared, right? So we start out with z equals 2 plus x squared plus y squared. If we substitute in y equals 2, the y squared becomes a 4. We get 2 plus 4 is 6 plus x squared, right? So that is z equals 6 plus x squared. Well, if z were y equals 6 plus x squared, we'd say, oh, that's a quadratic equation, that's a parabola. The fact that z equals y makes z isn't y makes no difference. It's still a quadratic with respect to z and x. So the point is, if we look at a plane where y is fixed, then it's a quadratic. Z is a quadratic in x. If we look at a plane where x is fixed, similarly, we have that z was a quadratic in y. So it's, we get quadratics in all these planes, just looking like that. If we're looking in one plane, take the cross section, it's going to look like that, right? So that's why it's a paraboloid. We don't need to know that for the problem, but it's good to keep in mind always what kind of surface you're working with, to avoid making simple mistakes. You might get some intuition for what the answer ought to be like. In this case, it doesn't really help so much because we're going to get some random gross answer, but it's good to at least have some idea of what you're doing. It helps with intuition when, handling future problems at least. So anyway, that's what S looks like, and what is the part of S above our region R, the part of S of which we actually have to find the area, look like? Well, it's some kind of weird blobby curvy thing. I don't know. It's two-dimensional, obviously. Blobby's the wrong word, but it's above R, which is here as we drew it before, and it's just some portion of it. It's not near the origin because R is not near the origin, right? It's just whatever portion of this paraboloid is directly above it. It's actually kind of, it's like on the underside of it, right? Because that's, that's what we're talking about. Some portion of the paraboloid, yeah, that doesn't really make sense. But like, it's sort of shaped like a saddle-y thing if you think about it, right? The part of a paraboloid above this annulus sector cutoff thing in the plane is going to look like a saddle thing, whatever. That's what we want to find the area of, okay? But we're going to do it mathematically. We're not going to do it visually. So, we don't really need to worry about what it looks like, but there it is. Okay, so there's a general formula for the surface area of, any kind of three-dimensional surface in math, and, the derivation of it is pretty nice. It's, the way I know to derive it that I just worked through again just now is using the cross product, but I won't go through that here since, it's not the most relevant thing. We just want to find the answer and know how to do these problems in the future. So the formula is, if you want the area of a surface that's given as z equals f of xy, okay, as we have here, right? It's a function of x and y. Then you integrate over the whole region, its whole shadow below it, right? In this case, that's r. You integrate over its shadow below it, which is a two-dimensional region. So it's a two-dimensional integral. And you integrate this thing that's root 1 plus the partial derivative of the function with respect to x, which we can write as dz dx squared, plus the partial derivative of the function with respect to y squared. And we have dx dy as the integrand because, or not the integrand, as the differential multiplying here because it's a two-dimensional integral. Now, if you've never heard of double integrals, this probably doesn't make sense to you. The way they work basically is just that you integrate inside and then you can integrate outside. You sort of treat it as like an integral of an integral, but that probably doesn't make sense if you haven't seen them before. So there's another way to do this problem, I guess, as a problem with surfaces of revolutions, but honestly, I've never used the surface of revolution method since I took Calc 1. Since then, if I wanted to find the area of something or the volume of something, I'd always just use this general formula that works for any kind of surface, even if it's all wonky and not, nice and smooth all the way around, like always, a surface of revolution, right? So this is the method I'll use. And hopefully, if the original poster is in a class where they haven't introduced this yet, I'm not sure whether this is a problem for Calc 3 or for Calc 1. But if they are, then they can tell me, and I can make another answer where I explain the other method. But I think this method's really the nicest way. So for anyone seeing this, who knows about double integrals or partial derivatives, I think this is really the best way to do it. And maybe it'll become clear how these work when I'm going along anyway. I'm not sure. I think it might be possible for you to pick this up because really these are, the simpler elements of Calc 3. There's some more complicated stuff in there, but yeah, these really aren't too bad. So, okay, let's see if this works out. So this general formula is this, as I said, and what I drew here was this is supposed to be a diagram of the intuition for the one-dimensional integral where you draw a lot of rectangles below the graph and you say, hey, if I add together all their areas, that's like summing each value of f times like how wide the rectangle is where that value is taken on, you know, pretending the graph of the function is just a bunch of steps, so every value is taken on over a little step, over a little interval, right? I sum those, that's the approximation of the integral. Well, the two-dimensional integral is like the same thing, except the domain is two-dimensional. So instead of summing, you know, like these line segments along the x-axis times their vertical height, you're summing like these areas of squares in the xy plane times their vertical height, okay? So, you know, it's going to look like a bunch of prisms that you're summing the volumes of. And otherwise, the mechanics are basically the same. Okay, random string marks, let me, for some reason happening, I'll get rid of, okay, no, I don't want that. Yeah, I'm not sure why I randomly made those lines. I'll just delete those, but they're not going away. I don't know. That's very strange. Okay, whatever. I'm going to the next page anyway. So yeah, so that's the, you know, I'll show you how to calculate the two-dimensional integrals. Basically, if you can write two squiggles and you know how to calculate one-dimensional integrals and you see an example of it, you can figure out how to generalize. And that's sort of a fun thing in math. When you learn a method you don't completely understand, but you realize you can sort of play with it anyway and get cool answers. And then later on, you can go back and see a proof of it, you know, see how, you know, I guess that's how all of calculus might be, depending on what course you're taking to some extent. If it's not proof-based, you know, you learn these tools, you're not necessarily clear exactly on why everything's true, but you can, you know, you can understand that later, but at least now you can apply them and get some cool results. So there's a place for doing both things, I think, in math, you know, starting out by understanding everything and then applying it, or doing it the other way around, and both can be rewarding in their own way. So, okay, so we have an integral, right? We want to calculate. We know what the formula is for z in terms of x and y. It's not what I wrote there. That's just, you know, the cross-section, just give intuition for why it's a paraboloid. The formula is z equals 2 plus x squared plus y squared. So we're going to plug that formula into this integral, integrate over our region R, and that's going to give us the surface area, right? This is the formula. Okay, so what happens when we do that? Well, and the reason I'm writing S here actually isn't just because they used it in the problem, the poster, but S is a standard notation for surface area, which is, you know, why the poster used it, whatever. So, okay, so S is this, double integral with that formula, as we said. So how do we plug into that? What does dz dx even mean if you haven't seen partial derivatives? Well, dz dx means like the derivative of z, okay, right? But z is a function of two variables, x and y. It's not like a function that just changes as one variable changes, right? It changes, if you change either variable, it changes a little. So what that means actually is it gets two derivatives at every point. The derivative, you can define more, but two basic ones. Dz dx means like, okay, what if I don't change y, but I do change x? What's the derivative? And dz dy is the same thing. I change y, but not x. So it's basically just like pretend that y is a constant, pretend that x is a constant. And then, you know, find the derivative with respect to every variable isn't a constant. And that sounds maybe complicated, but to do it in practice, it's actually really simple. If you wanted to find the derivative of the function xy, or yeah, I'll just use the examples that, okay, let's undo whatever I just did there. No, redo. Okay, weird. All right, that's not working. All right, apparently undo doesn't work on this thing, so I'll just fix that. Okay. All right, good. Okay, whatever. All right, so yeah, so what do we have here? We have, as we said, we have that the equation is for the surface is z equals 2 plus x squared plus y squared. So what if this were just a function of x? What if we pretended y were constant, like instead of y, it were like c or k or big C, whatever, you know, something we would consider to be a constant? Well, then the derivative would, of course, just be, and this is dz dx. The derivative, well, 2 is a constant, y squared is a constant, so their derivatives are 0. You know, by linearity, we add those to the derivative of x squared, which is, of course, 2x. All right, and by symmetry in x and y, dz dy is then 2y, right? So that's all these partial derivatives are. This concept of partial derivative is just like, okay, whenever there's a function in two variables, that's like a derivative that's differentiable. You know, you can take its derivative if you pretend like one of the variables is a constant, which is sort of equivalent geometrically to like looking at a cross section, right? But algebraically, well, all you really need to know is, okay, like pretend one is a constant, and take the derivative with respect to the other one. So basically, treating the other as a constant, factoring it out, or if there are terms that just have that other one, just getting rid of them because derivative of a constant is 0, That's what we did here. Derivative of y squared is 0. If we had like a factor of y, though, we just keep that factor because constant factors stay. Constant terms go away, right, when you're taking the derivative. So we treat y as a constant. That's how we get the derivative with respect to x. Same thing with the roles reversed for dc dy. That's what these partial derivatives are. It's really, it's an intuitive concept if you think about it a bit, because what you're basically doing is saying, okay, it's like, oh, I have, the heat index depends on temperature and depends on humidity. It's some function of both, whatever. How does it change if temperature stays the same but humidity changes? Then what about if that's the other way around? And these just give you a way of quantifying what those both are by just, using the fact that, okay, if one variable doesn't change, well, mathematically that means it's a constant. So I can use what I know from single variable calculus, because then I really have just the dependent variable, a constant, and only really one independent variable now, which is what lets you apply single variable calculus. I don't know if that quite made sense, but basically ignore one of the variables, treat it as a constant. That's how you do partial derivatives, which is the first thing you will learn in Calc 3 if you take that, or if you're already in that class. Again, I don't know what the original poster was in. Okay, so anyway, you have, this is how, maybe I'm giving too much intuition on various things here, but I want to make sure that some of these, that I cover some of these things to just clarify this for anybody who's watching this and doesn't know what double integrals and partial derivatives are even, so it won't be completely useless. Okay, so maybe I should post another answer where I just explain that, using the calculus method, even though that's kind of, it's not as general and sort of messier, and so I'm not sure if I'll do that. But okay, so anyway, so we plugged that into this, right? So we said, okay, so this is what this formula says, and if I didn't say before, a cross product is how you prove this. It's cool. It's intuitive why the Pythagorean theorem comes up. It has to do with the magnitude of a vector, and that vector happens to be 1, like negative dz, or rather, it's actually like negative dz dx, negative dz dy, comma 1, something like that. It seems pretty weird, but you end up with that vector in the proof, and then you take the norm of it. That's how you get this root something plus something plus something squared. These are all squared here, but anyway, assuming this is true, we plug into it. We plug in 2x for the derivative with respect to x, 2y for derivative with respect to y, and plug them in. Now, what is this? Okay, we're integrating over a region R, root 1 plus 2x squared plus 2y squared. Simplifying that, that's just 4x squared plus y squared, right? And that should be a d there that got deleted. Okay, so now this is nice because this is just an integral in x and y, right? We've gotten rid of the third variable. That's the point of this formula. It says, okay, if we know what the function's like in terms of x and y, right, then we do these partial derivative thingies to the function. We get something, which makes sense that would be relevant, right? It tells you like how much the function, it sort of tells you how it's sloped. I mean, that's exactly what it tells you, right? It tells you how the graph is shaped. How does it, slope up when x changes but y doesn't? What about the other way? So basically, how is it shaped? That tells us like how much area, surface area we get for each bit, each piece of area in the xy plane, right? A good sanity check here is if dz dx and dz dy were both 0. That is, like if z were, a constant function of x and y, which would just make it like z equals 3 or something like that. It would just be a flat plane parallel to the xy plane, right? In that case, clearly, the surface area above any region is the same. There's just like it just shoots right up, right? For z equals 3, the surface area is the same as the corresponding surface area in the xy plane. And indeed, if we plug into this, we'd say, well, in that case, dc dx, dc dy are 0, root 1. Okay, then we just get integral of dx dy, which says like, we just take the area of the region R, that is the area of the surface. But if the surface is slanted at all, then it's going to have more area, right? Like if we take a square and then we like, draw a shape above it that like slants up, it's going to have extra area, right? It's like it's bubbled up, right? A sphere shell above a circle is going to have more area than the circle, right? It's pushed up, it's convex, right? So and even if it's, has some concavities, it'll still be convex in enough places that it's always going to have more area. This, if you prove this formula, then you have a formal proof of that. But basically, because it can slant around, we get more area than just integrating the cross-section of the xy plane. We have to integrate something times the cross-section of the xy plane. This formula tells you what you have to multiply each area unit dx dy and the cross-section r by to get the area of the actual piece of the surface, S. So, all right, so S is whatever. We plugged into that formula. We have something nice in X and Y, but how do we integrate this? Well, I know it's kind of annoying. It's a double integral. You may not even know how to do those, but there are some nice ways to handle those. So let's go to the final board and see how that works. Okay, so again, this is our formula we came up for the area of it. We're integrating over R, root 1 plus 4 times x squared plus y squared. Okay, and that, yes, that's right. Okay, cool. So one thing we can do, which you may not have encountered yet, I guess even if you just took calculus, you probably encountered polar coordinates, at least in pre-calc, and you did that for a reason. If you did limicons, that was for no reason, because they never come up again in your life unless you, I don't even know if there are limicon experts, but you know, some stuff in pre-calculus is genuinely useful, like polar coordinates. They really help for integrating a lot of things in calculus, because some things are more circly. And it turns out, as one might expect, that using like rectangular things to find the areas and volumes of round circly things is just not really the best thing to do. You know, it's like, you know, to be fairly literal, putting a square peg in a round hole, right? I mean, it's literally that. So, you know, polar coordinates, if you recall, are alternate coordinates for the xy plane. They make it the r theta plane. Instead of labeling a point by where it perpendicularly projects to along the x-axis and along the y-axis, you label it by its distance r from the origin and by its angle theta counterclockwise up from the x-axis. So then it has coordinates r and theta, and it turns out that there's a way to do double integrals. Well, you know, instead of just using x and y, you use r and theta as the parameters and define the integral with respect to those. And the idea basically is everything's the same. You just like if you can rewrite the function in terms of r and theta, which in this case we can, right? X squared plus y squared is r squared, you know, the distance squared from the origin, right? The function is just a function of r in this case. That's not always true. Well, it is always true. It's a function of r and theta. Here, it's just a function of r, right? That's nice. You have to rewrite the function itself. You also have to change what you're integrating, right? You're integrating over the same region, okay? We're talking about the same integral here, right? But we have to change like the parameters we're using because we've changed our variables. Just like when you do a u substitution, you know, you change your parameters, right? You know, there are other ways. That's the best way to be careful about it, right? If you do, you know, have 1 to 2, and then you do u equals x squared, well, then now you're doing 2 to 4, right? Same deal here when we're changing coordinates to polar coordinates. Okay, well, yeah, but then there's one other thing we have to change. We have to change this differential here, the d part, because in polar coordinates, dx, dy, well, that's in terms of x and y. That does give the area of one area element, that is like one infinitesimal piece of the xy plane that we want to take the area of. But here, we need to express that in terms of r and theta, because they're the variables using. If we're doing everything in polar coordinates, we need to find some way of expressing the area of that piece in polar coordinates too. And it turns out that RD theta works for that. Yeah, it sounds funny, RD har har, but basically you have, if you look at like the region in the plane between two radii and between two angles, right? So like, here's the first angle theta, and we'll zoom in here to write this better. Here's the second angle theta plus d theta. And this is like the same shape that that r is actually, right? But here we're talking about an infinitesimal version of r. I mean, big R. The region we started with in the xy plane, it's bounded by two circles, the annulus, except it's also restricted to a sector by two lines. The lines determine the bounding angles, and the circles determine the bounding radii. So that's r, and then the higher circle would be radius r plus dr, right? So it turns out, if you have a little thing like that, basically, if dr is really small, so the radius is hardly changing, and d theta is really small, this is basically a rectangle. So you actually, to find the area of this thing, you'd actually just, do like the product of the two sides. And well, what is that? Well, dr is this thing. This thing is dr, right? That's where it came from. We're looking at the distance between the two radii. This other thing's a little harder, but still pretty easy. The length of that is basically, well, it's on a circle of radius r, right? But then the angular length of it is d theta, right? That's the angular change between, That's the angular change in this region. So if we know from trig or algebra 2 or pre-calc or whatever that if you have a part of a circle of radius r and an angular width of theta or d theta, whatever, then the length of it is the radius times that angle, right? That's how radians are defined. That's why, that's the definition of formal definition of angle. So like the length of this then I'm saying is r d theta. D theta is the angular change of that piece of the circle, and r is the radius. If we looked at the bigger circle, it would be r plus dr times d theta, but dr is so small that dr d theta can be ignored. It's the same kind of argument you would use, ignoring products of d's, products of differentials, that is, you would use in one variable calculus to do stuff. So basically, r d theta, r d theta is that, so r d theta times d theta, that's what we get here. That's a short, quick, intuitive derivation of why we use that instead of dx dy, or we're doing polar coordinates as the area of a tiny piece. So, just as we can say, oh, we can get the surface area, we can evaluate this double integral. This works for any double integral. It's not just about surface areas, by looking at all these little pieces of the xy plane, multiplying their areas, dx dy, by the function of x and y at them, well, we can also just look at all the little pieces, but think of them in terms of r's and thetas. Say, hey, what are the areas of these little pieces in terms of changes in r and changes in theta? Well, the r d theta. If dr is the change in r, d theta is the change in theta, we multiply those by this function of r and theta. Okay, so that's that's just a little tangent on how polar coordinates work. Okay, again, obviously, it could be a lot less long-winded if I knew what your time limit was. If I'm working with you, but I just want to have something for everybody here. Obviously, you can, people, I assume, can skip through things that I assume Wyzant has the capability to skip through a video, so they can skip through things they know. But, I'm just clarifying things for people who, might want to hear more about particular things. This is a benefit of tutoring, as opposed to teaching, that when you're tutoring, you can find out exactly what someone wants to hear more of and what they don't, when you're tutoring one-on-one, and then stop talking about the things they don't, talk about the things they do. Whereas with teaching, which is more like what this is, a video for everybody, you have to cover everything or just not cover things for anyone, right? Okay, so anyway, so so that's this integral. We saw why polar coordinates worked. Okay, but what are the bounds? Well, if we look back at our region R, remember I said it is like, it's like that little region there, except it's non-infinitesimal, so it's not really like a rectangle, it's a curvy rectangle. Okay. Well, but the fact that it's like that region there is actually helpful here. It's helpful in writing the bounds. It's, it's the reason that polar coordinates are applicable, because it's a curvy region. It's defined by circles centered at the origin and lines through the origin, which are exactly the same things that define polar coordinates. They are to polar coordinates as x equal lines and y equal lines are to Cartesian xy coordinates, named after Descartes. Polar coordinates named after polar bears or something, I don't know. Anyway, so you look at the integral, what are the boundaries here? So the outer integral corresponds to whatever variable we write second. That's just a convention to help us keep track of things. Doesn't really matter, but that's how you end up writing these things. You'll get the wrong answers sometimes if you don't do that. Just a way to keep track of things. We could do it the other way, but this is less confusing. I think that's just how mathematicians and physicists and everybody do it. So we'll first write the bounds of what theta can take on. Well, in our region R, if we recall from board 1, it looks like this, right? And I don't know why it's randomly drawing things. This is very strange. I don't know why. I think this is some problem with the Wyzant whiteboard. Okay, well, there we go. It's gone. Okay. So probably I'm just doing something that makes it hold down. I don't know why. Okay, so anyway, this region is between angles of 45 degrees and 90, i.e. pi over 4 and pi over 2. So those are going to be the bounds on theta, right? That's what we're integrating over. Theta ranges from pi over 4 to pi over 2. R, on the other hand, ranges from, remember, root 2 to 2, not 2 to 4, because that's r squared. Okay, right, and we're integrating over all points with the r in that region, radius in that region from the origin, and theta, angle from the x-axis, positive x-axis in this region. So those are our bounds in the integral. Root 1 plus 4r squared is the integrand, but then also this r, because that came with the differential, so it's always going to be there whenever we integrate anything in polar coordinates, but it's also going to be something we have to treat as part of the integrand now. That's what that means. Whereas dr and d theta are just differential things. we just associate dr with the inner integral and d theta with the outer integral and compute things. So how do we actually compute this now? It's a double integral. Maybe you haven't seen this before. I'll explain how this works. Okay, so we can do one thing you can do with basically, if anything looks notationally right in calculus, it's usually valid. You see rules like, if the inverse function rule dx dy is like the reciprocal of dy dx. That's true. You just have to make sure that you're like applying things at the right points, right? And like, all these theorems, dx over dy doesn't even mean anything, right? Like, what is dx? What is dy? Like, they're infinitesimals. What is an infinitesimal? There's no infinitesimal, right? That's why 0.9 p is equal to 1. But, and there are ways of grounding calculus and infinitesimals by rigorously defining them and stuff. But the standard way of defining them, there are no real infinitesimals. They're just they're just tiny things and tinier things. So nothing that's actually infinitesimal but non-zero. But these notations that pretend they're infinitesimals, even if you're not using a mathematics grounded in them, can be really helpful in getting intuition. Basically, anything you get from them turns out to be true. The same thing can happen with infinities often. You can do all kinds of arguments and get true results. Even Euler did this. He wasn't as rigorous as people were later. The famous mathematician Euler, to get like the proof that the sum of 1 over n squared, over all natural numbers n is pi squared over 6. He had some non-rigorous infinity argument, but basically my point is just that on that tangent is that you can make non-rigorous arguments with symbols, and if things kind of look right and you're using cool, nice manipulations, often you'll get things that are true. Not a proof, but it can be very useful. So if you're trying to figure out what a double integral is, then you say, well, it kind of looks like I'm integrating an integral, right? This function here, this whole integral, well, it's a function of, it depends on theta, right? Well, actually, it doesn't. It doesn't depend on theta at all, right? So then you could say, well, if it doesn't depend on theta, I can pull it outside of this integral, right? Integral of something d theta is a constant. And that's exactly right. We take that integral and move it here. So all of this is part of the r integral. And then we're gonna multiply it by the theta part, which is just integral of d theta, because this thing here is just a constant with respect to theta, right? So it doesn't have anything to do with theta, so that's, we can break this up into a product of two things, the integral of the r times the integral of the theta. Because this integral is just a constant with respect to theta, so this would just be that constant times integral of that d theta, which is, of course, just the difference between the two endpoints. Integral of d theta from pi over 4 to pi over 2, just like integral of dx would be, variable doesn't matter, just a notation, is pi over 2 minus pi over 4, which is pi over 4, of course. All right, so the theta part is actually easy. Intuitively, that's because this thing is totally symmetric with respect to all the angles it has to do it. It has to deal with from, 45 degrees to 90 degrees, nothing's changing, for either the paraboloid or the cross, the shadow, the projection in the xy plane. The r part's a little harder though. We now have to integrate root 1 plus 4r squared r dr from root 2 to 2. Now, r might trip you up a bit, but remember, notation never matters. I had a mentor who would use rabbits all the time instead of variables to emphasize this. Then I had another professor who would, get really annoyed if we ever used the wrong letter to represent anything in number theory class because, there are standards for everything. So people have different philosophies, but, I think I like to say notation really doesn't matter at all. So if this were x, then you'd say quickly, hopefully, this is a u substitution, right? Because root 1 plus, well, forget about the root, 1 plus 4r squared, this is a function of root 1 plus 4r squared, except for that factor of r, right? What you have to integrate, is. But 1 plus 4r squared, where that's a quadratic, derivative of a quadratic is like r, specifically in this case, it's 2r. Okay, but that's what we have here as a factor, right? That's exactly what we can do with u substitution when we have a thing, or some function of a thing whose derivative, and then multiply by the derivative of that thing, basically. Up to a constant factor, constants are always okay, right? That's what u substitution lets us do. It lets us suck up the derivative into the differential and, simplify the thing, basically just integrate the function that we had. Here the function square root, we have square root of a thing times basically up to a constant factor, the derivative of that thing, the thing being root 1 plus 4r squared. So we can write square root of u times, well, is r the derivative of u? No, actually 8r is the derivative of u, right? 1 goes away, 2 times 4r is 8r. So we'll just multiply by an eighth so that we can multiply by an eighth and then multiply by 8, right? If we do that, we have an eighth outside, then that allows us to put an 8 inside because 8 and 8 cancel. and 8r, that we can suck into du, right? 8r dr is the same as du because u is 1 plus 4r squared. Right, so 8r is just the derivative of that. Okay, so the 1/8 is just to compensate for that 8, right? We see that this r integral is just the same as 1/8, and then integral of u du. But as I mentioned before, of course, when we're doing u substitution, we have to change the limits because, you know, we're talking about a different thing. We're changing units, basically, right? So, okay, and again, it's doing that. Okay, I think I just double-clicked or something. Maybe that's a thing. I don't know. I have to look this up. Whatever. Okay, anyway, 9 to 17 are now the limits because if we apply 1 plus 4r squared to 2 and 2, then that's what we get. Okay, now this is a relatively simple integral. This is just a power rule thing, right? U to the 1/2. Okay, that's, you know, integral of that is going to be 1 over 1/2 plus 1. U to the 1/2 plus 1, that's 3/2, 1/2 plus 1. So it'd be 1 over 3/2, that's 2/3 times u to the 3/2. Constant can come out by linearity, you know, and we're evaluating this thing at 17 and 9 and subtracting. I'm not going to bother finding what that is. You know, it's some gross irrational thing, of course, and then multiplied by pi, which is transcendental. So, you know, whatever final answer, maybe you want, your teacher wants an approximation for this. Anyway, this is how you do this kind of problem in general using double integrals. It's, you know, the basic idea of the double integrals is you can do like, you know, pretend it's like an integral of an integral and go from there. This will, you know, whether you end up doing it in polar or in Cartesian, where in polar you would use this thing as the differential piece. It's called the Jacobian, formerly after a guy named Jacobi. Then, yeah, you just, you know, you integrate, you do like one integral at a time. Yeah, and then when you're doing one integral, use all the same techniques as before, use substitution or integration by parts or whatever happens to be most amenable to that integral, trig substitution, whatever. Anyway, this is an example of integrating a surface. Not a particularly, you know, important surface, but after all, you know, it's sort of cool that a paraboloid, you know, with a paraboloid you get pi, well, maybe that makes sense because of the rotation, but you also get weird irrational things. And we didn't start with anything really weird. Well, we did start with a circle of radius √2, so that's essentially where they came from. If you think about it, if we had started with like, if we went from all the way to the origin, 0 instead of 2 is the radius squared of the inner circle. Then this would be a 0 instead of, or it would be a 1 instead of a 9 actually because of that 1 there. And then this thing 17 would be, would be what it was still. So we would, then we'd still end up with a weird irrational thing just from x squared plus y squared equals 4. It seems like it's kind of nice, you know. And if we had x squared plus y squared equals 1, then, you know, then we'd get 1 as the upper limit. Or, yeah, we get 1 as the upper radius limit initially, which would turn into 1 plus 4 times 1, so 5, and we'd end up with like a 5 to the 3/2. So it's weird. We get cool irrational things, you know, these radicals just from a simple setup. So paraboloids need irrational things to find, you know, surface areas of them. Go figure. That's kind of cool. You know, you might not have thought of those as coming up from paraboloid area problems. I certainly wouldn't have initially. You know, and it's only square roots, which is essentially related to the fact that, well, yeah, it's really because of surface area. So not the fact that there's a square and a paraboloid. So anyway, you know, it's maybe sort of cool. There are shapes you might care a lot more about, like cones or spheres, and you can use the same method, you know, see what happens. You would definitely want to use polar coordinates, but you can set up the same thing if we're like finding the formula for the surface area of a sphere, right? If you haven't seen a proof of that, you know, this method gives you a way to prove that. So that's, you know, that's a good method. If you can do these partial derivatives and double integrals, if those make sense. And this is a method for dealing with all kinds of surfaces, whether or not they're surfaces of revolution, even if they're weird and wobbly. This, you know, setting up this double integral, you find the region R, you find out, you know, you write the surface as z equals f of x, y, take its partial derivatives, plug into our formula here, and just keep going, you know, until we can maybe use polar coordinates, or maybe it's already nice in Cartesian coordinates, probably polar coordinates, because, you know, if we use Cartesian coordinates, we're going to end up with something like root, you know, we're not going to be able to collapse an x squared plus y squared or something. And, you know, roots of functions can be really hard to integrate. Like even, you know, root 1 plus x squared is really annoying to integrate. The simplest way, I think, is to use like a trig substitution. And that, you know, there can be several steps to that. So, you know, things are usually going to be simpler if there's a way to jump into polar coordinates. The nice thing about polar coordinates is you have something that looks gross like root 1 plus 4r squared. Like I said, root 1 plus r squared, root 1 plus x squared, even that's hard. But this extra r that comes with a Jacobian often makes things easier to integrate in polar coordinates, because it can like let you do this U substitution. So yeah, and if you're doing this in Cartesian coordinates in this case, it would be even worse than this. It's not like that, this r is why polar coordinates are useful. I'm just saying that like, often you have something that looks sort of gross, but it's actually less gross than it appears because of that thing that comes up with polar coordinates. So, that's just sort of the mechanism by which polar coordinates avoid being really gross. But the point is basically some things work better in polar, some things work better in Cartesian. Either way, use the appropriate thing to handle this double integral, and this is how you deal with surface areas. And, the method for dealing with volumes is basically the same thing. There's just a different formula to use. It's a lot simpler, but again, you'd want to use, if you have something that's a surface of, that's, the volume under a surface in 3D with the surface is equal to f of x, y, then you'd want to, just integrate under the, then you'd want to, integrate over the region R again, but here you just, instead of this complicated thing, you just do, the height of it, just the value of the function, instead of this square root thing. You'd replace it all with the value of the function, but you still have a double integral because you want to go over the whole shadow under it. And you might want to use polar depending on what the shadow is shaped like. For this paraboloid, we could do the same thing with volume basically. So like I said, instead of the square root thing, we just use the value of the function because that gives the height at each point, which is what you need for the volume. And then, so there's much the same. So there's not really much about, we haven't really done anything with surface area here, except when we were explaining how to visualize the problem in the beginning. All we've been doing is integrating over two-dimensional area, nothing about like curved area, because we didn't actually analyze how to derive the formula. If we analyzed how to derive the formula, we'd have to, think a lot about these curved area, but knowing the formula, you don't really have to think about curved area at all, right? You just look at the simple function, take partial derivatives, do the double integral, maybe by using polar coordinates, maybe by using Cartesian coordinates, and calculate it out and get something like this as the answer. Anyway, that's about all one can say about surface area, how you solve these problems in general. I guess the notes are there if one wants a short version. I assume they could have just, skipped through this video to see the notes. But maybe I'll add a note about this if I can write something when I submit this, that if you just want to see the equations, you can just, skip through, but I add more and more explanation for whoever wants it. And you can see as much as or little as you want. And if you found some of this explanation helpful, consider checking out my profile, or even if you don't, if you just want stuff for free, then look at other videos that I post on, in answers to people's questions. Anyway, okay, take care. I think that's pretty much all you can say about this. Bye.